All right, here we are. It's Wednesday the 28th, and we're staring down the barrel of our last topic or topics. And I'm a little sad to see the semester end, but also happy to get through this and move on away from COVID and all these videos and meetings in the dark of Zoom. And I'm sad to say, well, for you all, that I won't be there in the fall. Normally, when I teach Calc 1, I also teach Calc 2. It's a 1-2 punch. But I finally got a sabbatical after 12 years this fall, and so I will be working on some of my own mathematics, doing research and trying to get published. And I will be back in the spring. And if you're an ME or you're doing the math minor, chances are you'll have me for Calc 3 or differential equations in the future. So I want to now try and tie all these things together before we do the fundamental theorem of calculus. And when I say tying it all together, we want to. So the goal here is to tie together Riemann sums, integrals, and antiderivatives. I normally do this sort of lecture much differently, and again, being inspired by Saul Kahn from the Khan Academy, I basically hijacked his video about this and put my own spin on it. But if you want to jump over and watch his, they're really old. It's kind of cool because in those days I couldn't figure out, and I totally remember that in those days you could only do YouTube videos for 10 minutes. So if you wanted to do something, you had to make like 3 videos, parts 1, 2, and 3. So the videos are 13 years old, but they're still pretty good. All right, so here's what we're going to start with. We're going to let S sub t be equal 4t squared be a position function. Hence it measures distance. We're going to look at the graph of this here. So here's the t-axis, because we're talking about time now, and this is distance, and so here's our and it's parabolic in shape. So here's our d equals s sub t, right? So 4t squared. All right, well, we know from our work all this semester that the derivative of this guy is 8t, and when you have the derivative of a position function, you get velocity. So we're going to call this velocity, and it's of course a line, and I'll let this be the v-axis, and it's a pretty steep line, but still it's a line. V equals AT. Okay. Now right away we see the relationship here. We have, if I gave you the velocity as AT, then you know that it's, and one of its antiderivatives is 4t squared. And in this case, the plus c that you get is just going to be 0 because of the initial condition 0, 0. So we're already looking at a function and its derivative or its antiderivative, depending on which direction you go in. Okay, so I wish the screen was bigger, but so we want to try and get a handle on how these two are related and bring the integral in here. So let's just assume for a second. Assume we're only given the v graph. This guy. Right? So let's say we're only given that the velocity of this thing, whatever it is moving, is 8t. So it has a constant velocity or a constant slope. And from this, let's say we want to find distance traveled. Right? Okay, so let's have a look at this. So we're gonna say we only have this graph on the right here. It's a cool red color I've been using lately. This one, no, this one. Yeah. Let's say I'm just gonna look at what happens for a really short instant here. We're gonna call this little short little time change here is dt. I should use delta t because it's a discrete, but I want to use dt for a reason. And we're just going to say, so dt is a tiny subinterval of the t-axis. Like so tiny, barely even measurable. And for all intents and purposes, along this little tiny subinterval, the velocity, which is up here, this is v sub t, is just constant for this little moment. We can assume it's constant or approximately constant. Okay? And so now, so I want to make sure I get this right. Remember, distance traveled by an object is what it's its speed, which is v sub t times distance, right? So it's speed over, so the distance traveled is speed times distance traveled, or no, time, sorry, the timestamp, what I want to say here. So it's speed times time. Why can't I say that? All right, so the distance traveled in this case is this little interval here, sorry, this height here times this little subinterval. So in the picture here, it's the area of the rectangle. Okay, the distance traveled, which is the area of the rectangle. Okay. And so now what we've done is, so let's just say we come over here to a little dt. And let me call this first point t naught and the second point t1. If you were going to compute the distance traveled, what would you do? You would compute s sub t naught, and you compute s of t1 and take their difference, right? Because that would be the actual distance traveled. So distance would be s of t1 minus s of t naught. But most importantly, and this is the part I was trying to tie together here, we've now taken the area under the curve of vt and related it to the curve of its antiderivative, s of t. Okay, well, let's say we wanted to find over a bunch of distances, or we wanted to go from, say, 0 to a number. Say, for how far do we travel over, say, 10 seconds? Well, you just have all these rectangles. Each one would have a little area, and that would be the distance traveled. So eventually, I went too far. Here we go. No. Eventually, I would accumulate all this area here in rectangular form. And so, what is it? It's the Riemann sum. Right? So the distance traveled is the Riemann sum from the graph of Vt. Right? Okay, so we have this, now we have this Riemann sum from k equals 1 down to n of what? Of v sub t times dt. It really should be delta t, but I'm just going to leave it like that. And so we define we define, so when you take the limit as n goes to infinity of this sum, we define the integral of, v sub t dt from t equals t naught to t equals t1 to represent the area. Oops. To represent the area, so v sub t times t, and so people are going, where does this integral sign come from? It's just a big S that's been stretched out, which stands for sum, and that's all an integral is really, it's a sum of things. Okay, and so this becomes what? It becomes the difference of the antiderivative, right? So we have the derivative, and the area under the curve of the derivative is the distance or the difference between the antiderivative. So, here we are tying it together. Okay. And I just love looking at it this way. I've never really thought of it this way before, and thanks to Saul. And again, if you feel like more of this, if you go to Khan Academy and do the search for definite integral, there's no R there. He's got part 1, 2, 3, and 4. They're a little old, but he goes into way more detail than this because I guess he wants to. And if I was teaching Calc 2, this is where we'd start, and we'd go much deeper. But this is the picture I want you to have in your head when you think about how this stuff is related, right? The area under the curve of whatever your function is, in this case it's a velocity function, equals the distance traveled along the curve of the antiderivative. So the area represents this, in this case, this little bit, where are we at here, 10. So it's going to represent from here to here along the curve, and from here to here, it's the area. So this area equals this. Okay. And yeah, so now we have what's called the definite integral. So the definite integral keep wanting to put the R first. It has the form a to b f of x dx. I'm just going to switch back to x, and this is called the lower limit of integration. This is the upper limit. This f of x is called the integrand. And dx is actually the little width of each subinterval. But it tells you what the integral, what the variable of integration is. And if f of x is positive on the interval a to b, then the integral represents the area under the curve. Okay. And so let's do an example here. Here we go. Let's let f of x be 2x minus x squared on the interval from 0 to 2. And we want to compute the area under the curve. First, let's make sure it's actually positive so that we are computing the actual area. I don't think your boss will be silly enough not to make it, but we'll check. So what does this have? 0? Is it 0 and 2? And at the vertex is that 1. Oops, a little crooked, but so it's at least it's positive. It's positive. It's positive. Come on, you can do better than that. Wish there was a parabola drawing tool. There it is. Okay. And so what we know now that the integral from x equals 0 to x equals 2 of 2x minus x squared dx is the limit as n goes to infinity of the sum from k equals 1 down to n of f of ck delta x, right? And so what's ck in this case? Sorry, delta x is 2 over n, ck is 2k over n, and so the area is approximated by 2k over n times 2 minus 2k over n squared times 2 over n. Lots of brackets and stuff here. And then I get 2 over n out front times the sum of 4k over n minus 4k squared over n squared. There's another sum here. Like that. Okay, so now we get 8 over n squared, the sum of the k's, minus 8 over n cubed, sum of the k squared. And then we have this minus 8 over n cubed, and I apologize for writing it like that, but we've gotten far enough along here. It's 3n squared plus n, but those always fall out when you take the limit. And now you let n go to infinity, and this gives us 4 minus 8/3. Which is 4/3. Okay. So the area under this curve is 4/3 units squared. Okay. Let's find an antiderivative for f. So an antiderivative for f is going to be, it's going to be what? X squared minus x cubed over 3. Plus a c. Okay. What does this look like when you graph it? And by the way, I'm making this up as I go along, so I'm just having a bit of fun here. I didn't think I'd get this far in my thinking, but here we are. Let's do this. Let's try and graph cap back. Well, let's c equals 0. Just do that for now. All right, so we're just going to graph. So when you plug in 0, you get that. When you plug in 1, you get what? You get 2/3. And when you plug in 2, you get what? You get 4 minus 8/3, which is 4/3, right? So up here, and sure enough, the distance traveled along this line, or sorry, yeah, the distance traveled along this curve which we showed before was just, so now we have to look at it differently. This is what? If you take cap f of 2 and minus cap f of 0, you get 4/3, right? So when you evaluate the antiderivatives and subtract them, including the c's, which cancel out, then you get the function value at that point. Okay, another cool thing we're going to look at that we need for the last sort of the sequel to this is this idea of average value of a function. And so you write AV of f, and if you take the integral from a to b of some function f of x, and you divide it by the length of the interval you integrate over, then you get what's called the average value. Okay, and this is a definition. So the average value of a function, and it's a mean of function values. But it really ties in, so let's look at what's the average value of our function here, right? It's going to be 1/2 times the integral of 2x minus x squared from 0 to 2, and that's 2/3. Okay, so the average value is 2/3. And this is the picture we need for the next bit. If you take this length here like that, and then you go up to 2/3, which is what the average value is, and you make a rectangle out of it, okay, the area of this rectangle equals the area under the curve. Okay. So the area, this is a note. The area of the rectangle with base AB and height. No, that's not right. Yes, height average value of f equals the area under the curve of f over AB. Then we need this. We need this for the next video. But I love this picture because it's basically said, all right, I'm going to take this area that's under the curve, and this curve doesn't have to be as symmetric as say parabola is, and find the average value, and that gives me a nice rectangular area shape that has the same area. So for example, if we had a cool function like this, get some green in here. Say something that went like this, off, and then we cut from A to B. Something needs to stick out a little more. There we go. And let's say we found this area here, right? So this is y equals f of x. So the area inside this state looking thing is the integral from a to b of f of x dx. But the average value is probably going to look something like this. I don't know. Maybe something like this, depending. Okay. And so this is going to be the average value of F. Times B minus A. All right. I think that's all I have. The next video will tie even more of this together with the fundamental theorem of calculus, and we will call it a semester. See you all in a minute.